Chapter 3, Number 15. The x and y components of a vector r are r sub x equals 14 meters and r sub y equals minus 9.5 meters, respectively. Find the direction and magnitude of the vector. And then, if both their rx and ry are doubled, how do you predict your answers to parts A and B will change? Verify that prediction by calculating the magnitude and direction for the new case. So let's sketch first and say we have our x and y axis, and we are informed that the vector r has rx equals 14 meters and ry equals minus 19.5. So ry is minus 9.5. I think I said 19, but 9.5. Whereas this was 14. And what we want is r, and then somehow we want to specify a direction, and I can do that sort of two ways. So to me, the natural way to do that is to specify that angle theta. And then we go back and we do some basic trig. So we say that r equals the square root of rx squared plus ry squared, the sides of this triangle. And so we get, right, our triangle is 14 meters and 9.5 meters. And you might wonder, but wait a minute, it was minus 9.5. But that's a component which is assigned distance. Triangles are, well, triangles, so they require actual distances. They require positive distances. So I have to take the absolute value of a side to make it back into a triangle. And then I can say, well, we just process this and we get the square root of 14 meters squared plus 9.5 meters squared. And I get square root 14 squared plus 9.5 squared, 16.9, which based on our two digits is really 17. By the way, you need to be careful because if you type this into the calculator with the signs, you have to say square root 14 squared is fine, but you can't put plus minus 9.5 squared, because if you do that, the calculator knows that in mathematics, the exponent binds more tightly. So this says square 9.5 and then negate it, and that's not what you want. So if you're going to put it into the calculator, you have to remember to also protect the negative sign with parentheses. Otherwise, you're getting something which is far less than 14 squared, which means that your side is less than 14. And you know that's wrong because the side of a triangle can't be less than, the hypotenuse can't be less than the other side. All right, now to get theta. All right, to get theta out of the purple triangle, for instance, we might say that the tangent of theta is sort of by definition, it's the opposite side over the adjacent side. So in this case, it's 9.5 meters over 14 meters. And then to liberate the theta, we would take maybe the inverse tangent. And the purpose of that is to free the theta. So the inverse tangent of the tangent of theta is, by construction, theta. That's what inverse tangent does. The price we pay is that anything we apply to one side, we have to apply to the other side. So over here, we'd have the inverse tangent of 9.5 over 14. And therefore, theta is the inverse tangent of 9.5 over 14, which is tangent 9.5 over 14, 34 degrees. So one way to specify the vector r, which is what we were asked for, is to say that r is 17 meters at 34 degrees below the plus x axis. to be honest, in my way of looking at things is we actually, by drawing the triangle and indicating theta, we were perfectly fine, and you don't have to actually write this verbiage. You have specified the triangle by finding r and finding theta, and therefore you specify the vector. There's sort of an alternate way of looking at this, which came up in the force table lab as well, so I'd like to sort of look at it and explore what it says. An alternate formulation can be arranged where we would get that that we don't have to build triangles and try and figure out which way the angles go and so on, and instead use that Rx is R cosine. I'm going to use the angle phi just to make it distinct. Ry equals R sine phi, and this works no matter where the vector points, which is kind of neat. And then we can see that this gives us similar truths, because we get that r is still rx square plus ry square, and we get that that tangent of phi is ry over rx, because it's always, tangent is always sine of the angle over cosine of the angle. And the nice thing here is we don't have to figure out who's associated with cosine and who's associated with sine. It's always x associated with cosine and y associated with sine. The price we pay is the angle is no longer the angle I've got drawn there. Instead, it's the angle as measured from the plus x-axis going counterclockwise. So this angle is phi, which is some weird angle, in this case bigger than 270 degrees. So that works out kind of, I mean, it's kind of neat, but it's also kind of weird. The r is the same, but I want to kind of look at the theta, or the angle. So we're going to get phi is inverse tangent of, in this case, minus 9.5 over 14, or the inverse tangent of about whatever minus 9.5 over 14 is, which is minus 0.679, and therefore phi is approximately minus 34 degrees. And actually, if we gave the angle as minus 34 degrees, we would be okay. Although it's not the angle I had drawn up there. To get the angle I had drawn up there, I'd have to take its partner from 360, so I'd actually add the 360 to get back into positive angles. And I'd say the total angle was 360 plus negative 34, or 326 degrees, measured counterclockwise in the plus x-axis. So I put that out there as an alternate way to do it, although there's some theoretical complications that you have to get your head around the angle. And again, any of these answers would be fine as long as you marked the angle that you were using. So the real takeaway is make sure to draw a picture and mark your angle so that I know what you're trying to say. And then you can do it any way that's convenient to you.